In the previous video, we looked at systems of linear equations and we solve them by graphing, right? But, graphing is kind of labor intensive, right? Um, and if you don't have, grid already made for you, you've got to make the axes and careful tick marks and everything. So it would be nice to have some other methods that might be a little bit quicker for us in order to be able to solve systems of equations. All right. And so the type of method we're going to use here is what we refer to as substitution. Sorry, let me change my color. Got the wrong one here. So we're going to use substitution. All right. So the idea is I'm still going to label my equations here. But what I'm going to do is I'm going to take one of the equations and I'm going to get one of the variables all by itself. So I'm going to take equation one, and much like I did in the previous video, I'll get y by itself. So I'm at 1 minus 2x. Okay. Now, the reason I chose to get y by itself is not because it needs to be y. I could have gotten x by itself. However, what we want to think about is which of the variables that are involved in our system are going to be the easiest to isolate. Well, if you have one of them that has a coefficient of 1 in front of it, then it's going to be easier to do the algebra to get it by itself because you're not going to have to divide by anything in order to isolate it in the last step. So that was the reason why I chose to isolate this y. So that's equation one. Now you take equation number two, and equation number two is 3x plus 4y equals 14. So you're going to write it, but instead of writing 4y, like is up here, you're going to write 4 times 1 minus 2x. Because remember that any ordered pair that is a solution to this system has to make the first equation and the second equation true. All right. So in this first equation, we realize that any ordered pair that works for the first equation, y is going to have to equal 1 minus 2 times whatever the x is. And so if we're looking for an ordered pair that's a solution to both of these, then the y value in equation number two should also follow that rule and be equal to 1 minus 2x. And so now we've got ourselves an equation that we can solve, right? Do a little bit of distribution here, right? We've got to simplify the left side. So 3x plus 4 minus 8x is equal to 14. And of course, 3x minus 8x, that would give me negative 5x plus 4 is equal to 14. And then we just set about getting x all by itself. So x is equal to negative 2. Now, whenever we solve a system, we need to report both the x value and the y value, of course. And so we want to go back and plug negative 2 back into one of the equations. But my strong suggestion here is to do as little work as possible. We have this manipulated version of equation number one that already has it the y by itself. So if you plug negative 2 back into that, then you're going to quickly figure out what y is without much work. So 1 plus 4, sorry, that should be a 4, is equal to 5. So our solution here is negative 2 comma 5. So what we did was we solved one of the equations for one of its variables, right? Got it by itself. Then we substituted the expression we found in step one into the other equation, right? This is really important. If you plug it back into the same equation, then all you're going to get is a statement that is true, but is totally unhelpful in figuring out what the variables should be. So you need to be plugging it into the other equation. And then finally, substitute the value you found in step two back into the expression you found in step one to find the remaining variable. All right, so looking at another example here, equation number one, equation number two. All right, we want to take our pick. What should we be getting by itself? Just like the last example, we have this y that has a coefficient of 1. So the best choice would be to take equation number 1 and get the y value by itself. And then equation number 2 would be negative x minus, all right, now this is really important here, it's minus y, but the y now is, we're saying, equal to 3x minus 2, so there's multiple terms. So it's vital that you put parentheses around the 3x minus 2. That way this subtraction sign applies to both of those terms. So negative x, and remember what we want to do here is it's negative applied to both of these. If you want to wedge a 1 in here, that's totally fine, if that is helpful. So it'd be minus 3x plus 2 is equal to 6. So we'll end up subtracting 2 from both sides. So negative 4x equals 4. So x equals negative 1. And then just like the last problem, use the equation where y is already isolated to figure out what the y value is that goes with it. So y equals 3 times negative 1 minus 2, which would be negative 5. So our solution is negative 1, negative 5. All right, so now in this example, I want to show two things. One is the variable that gets isolated or that is isolated doesn't have to be y, it can be x instead. And secondly, if some of the work is already done for us, then we can just be happy about that and kind of move on quickly. So we have equation 1 and equation 2. This x is already by itself in equation 2, right? So no need to do any work in getting a variable by itself. Essentially, step 1 of this process is done already, right? Without us having to lift a finger. So now what we'll do is we'll take equation 2 with x isolated and we'll plug that in to equation 1. So equation 1 said negative 2 times, we've got 3y minus 3. That will get plugged in for the x right here. Plus 5y equals 6. And of course, we have some nice distribution to do here with my negative 2. So that left side becomes negative 6y plus 6 plus 5y is equal to 6. So negative 6y plus 5y is negative y. Subtract 6 from both sides, you get negative y is equal to 0. And of course, that means just that y itself is 0. Don't really need to show this last step, but there you go, y equals 0. And that's fine, right? Nothing wrong with x equaling 0, nothing wrong with y equaling 0. So we then plug it back into equation number 2. 3 times 0 minus 3. So the solution is negative 3, comma 0. All right. We're going to do a couple of more equations together, or systems of equations together here, and then I'll have a number that you can practice with. All right, but I want to do this one together for sure. This one's potentially a little less friendly looking. Um, the first thing you might notice here is that it doesn't matter if we're talking about equation number 1 or equation number 2, um, there is no x or y that has a coefficient of 1 in front of it. Okay. If that's not the case, that's okay. Just make sure that you try to isolate the variable that has a coefficient that makes it as easy as possible to get it by itself. So here's what we mean. In the end, if you are getting one of these variables by itself, the last step is going to be to divide by whatever coefficient is in front of that variable. Well, if you think about, would I rather divide by 3/4, -6, -16, or 2? I think the answer is clearly I'd rather divide by 2, right? Numbers turn out pretty nicely when you divide by 2. They turn out less nicely when you divide by things like 6 or 16 or even 3/4. So the best choice would be take equation number 2 and work on getting this x all by itself. So we'll add 16y to both sides. 2x is equal to 8 plus 16y. We'll divide by 2 on both sides. So x is equal to 8 over 2 plus 16 over 2y. So x is equal to 4 plus 8y. All right, but now we're going to approach this. It was a little harder to get x by itself than on the previous questions, but we'll approach the rest of this the same way. We're going to take equation number 1, and we are going to plug this in where I see an x in equation number 1. So it'll be 3/4, but instead of times x, it'll be times 4 plus 8y. And then minus 6y is equal to 3. Now, when we distribute the 3/4 through, remember that the 4 and the 8y, they're in the numerator. But you can always, if it's helpful to you, as you do that distribution, 3/4 times, it could always be 4 over 1, right? If that's helpful. 3/4 times 8y over 1 minus 6y is equal to 3. Now let's see what happens. We do have some nice reducing that can happen here. Divide by 4, divide by 4. Here we can divide by 4 on top and bottom, and that leaves us with a 2. So after all that canceling, we end up with 3 plus 6y minus 6y is equal to 3, which strangely then simplifies to 3 equals 3. Okay, so when something like this happens, what does it mean? Well, the fact that we ended up with a true statement at the end and we didn't have to specify what our y value was. That means that it doesn't matter what y value you choose, that you can find a solution to this system. So another way of putting it is there are infinitely many solutions. Okay? The fact that the y's go away means you can make this equation true if you let y be 0, if you let y be 1, if you let y be 203. Okay? It leads to a true statement that's always true no matter what y is, so there must be infinitely many solutions. All right, here's another example. All right, of all my choices here, what would I rather divide by at the end of my problem? 4, -12, +3, or -1? I think I'd rather divide by -1 at the end of the process of getting a variable by itself. So I will take equation number 1 and work on getting y by itself there. So negative y is -4x plus 5. Divide by -1 on both sides. So y is equal to 4x minus 5. And we know the drill now. We're going to plug 4x minus 5 in for the y value. So we get -12x. We're going to distribute that 3 through to both terms. So plus 12x minus 15 equals 7. So it's kind of similar to what happened in the last problem. -12x plus 12x, they cancel each other out, but then we end up with this. Okay, but this is a different situation. Last time we got 3 equals 3, right? A statement that is always true. Here we get -15 equals 7, a statement that is always false, of course. And so the idea here is that we ended up with a false statement, and it didn't matter what we let our x be. The statement was always going to be false. And so when that happens, that's like when we had those two parallel lines when we were solving by graphing. That's when we have no solution. So here's what could happen when we're solving our systems. There could be exactly one solution. Number two, if in the process of solving we get a statement that is true for any value of a variable, then there are infinitely many solutions. And then number three, if in the process of solving we get a statement that is false for any value of the variable, then there is no solution. All right, so the rest of the problems on the next 2 pages are just practice for you. So you'll notice A through F. So A, B, C, D, E, F. So I want you to pause the video, um, try these yourself, and then unpause the video and see if you and I are getting to the same things. So when you unpause, I'm going to work through them, but I'll work through them at a pretty decent pace. But then you can check your work against mine. All right, so for this first one, we're lucky enough that in equation number 2, y is already by itself, so I can jump straight to the step of plugging it into my other equation. equal to 5. Lost my train of thought there. So we're going to distribute. So negative 6x plus 9 is equal to 5. So negative 2x plus 9 equals 5. So negative 2x is negative 4. So it looks like my x value is going to be 2. But of course, we can then take equation number 2 and plug that directly in for x, which gives us a solution of 2 for the x and 1 for the y. In part B, none of the coefficients in front of the variables are just a positive 1. So it looks like the best I can do here is take equation number 2 and solve it for y, because I'll just have to divide by negative 1 in the end. So negative y divided by negative 1, negative 2x plus 8 divided by negative 1. So y is equal to positive 2x minus 8. Plugging into the other equation, right? It's always the other equation. Take our 2x minus 8 in for y. And then we will simplify on this left side. So 13x minus 40 equals negative 1. Add 40 to both sides, so 13x equals 39. So my x must be equal to 3. And then we plug back into the altered form of equation number 2, right? So it's equation number 2, but after I've gotten y by itself. 2 times 3 minus 8 is negative 2. So our solution is 3 comma negative 2. All right, part C is more like the part A we did. We've got one that's nicely set up so that I don't have to do a whole lot of work, right? So equation number 2, y equals 3x. I can plug 3x directly in for the y in equation number 1. So 2x minus 21x is equal to 0. Negative 19x equals 0. But that just means x equals 0, right? So x equals 0 is it's the x value of our solution. And then we take equation number 2 and say 3 times my x, right, which of course is 0, so put it right in there. So that means y is 0 as well. So nothing wrong if the ordered pair that is our solution happens to be 0, 0, or at the origin. It's not a problem at all. In part D, the best choice here, of course, is to get this y by itself from equation number 2. So here's equation number 1. Here's equation number 2. So negative 3x plus y equals negative 4. Add 3x to both sides. Made a mistake there. It should be a -4. So let's say 3x minus 4, and then plug that back into equation 1. Always putting these multiple terms in parentheses, right? Want to really make sure we do that. And as I distribute, I'm distributing the negative through to both terms. So -6x plus 8. So -x plus 8 equals 9. Subtract 8 from both sides. So it's -x equals 1, but x isn't by itself yet, right? So we got to divide by -1 on both sides. So x equals -1. And then plugging that back into the altered version of equation 2 gives me -7. Okay. Part E, a little more straightforward than the last one. And it is, but I like doing ones like this because notice that in equation 2, when we have 4x minus 4, and then you plug that into equation 1, it's just so easy to get lazy with this minus sign. So we're subtracting off, but because there's no number in front of this y, it's tempting just to write 4x minus 1 right here. But remember, you have to put it in parentheses, right? Because that minus sign has to apply to both of the terms that are taking the place of y. So 2x minus 4x plus 4 is 3. 2x plus 4 is 3, and then we'll subtract 4 from both sides. Now, in many of the problems we've done, I've let you have nice number answers, right? There's nothing wrong with getting a fraction answer, right? So don't be alarmed by that. So x is equal to a half here. And then in equation number 2, 4 times a half minus 4. So y is 4 times a half, of course, is 2. So y equals -2. All right. So one thing I just want to emphasize in this very last one is that um, trying to find um, the most efficient way of getting one of the variables by itself, the one that requires the least amount of work, is just to simply help us have easier algebra to look at, right? You can isolate any one of these. So on this one, just to illustrate this, let me do the following. Let me take equation number 1 and equation number 2, okay? And I am going to get this x by itself instead of getting, say, this y by itself in equation number 1. Okay. I just want to illustrate that it all works no matter what. Okay. We'll just make a little comment up here that I'm doing this the harder way by isolating this. Okay. So if I did it that way, I would add 2y to both sides. And then, of course, divide by 3 on both sides. So the reason we're not big fans of getting x by itself when you end up having to divide by 3 is because while 9 divided by 3 is nice enough, you're going to end up with a fraction, 2/3 y. Okay? Now, that's not the end of the world. We can always then go, well, let's rewrite this, x equals 3 plus 2/3 y, and then do equation number 1. So it'll be 2x, right? So plugging this in, 2 times 3 plus 2/3 y minus y is equal to 5. So 6 plus, now this is 2 over 1, right? Times 2/3. So that's going to be 4/3 y minus y equals 5. But we're going to want to put these y's together, right? So 4/3 minus 1y, well, that's the same as 3/3 y, right? So when I go to simplify this, it'll be 6 plus 1/3 y is equal to 5. Subtract 6, subtract 6. 1/3 y equals -1. And then, of course, if you want to get the y by itself, multiply by the reciprocal on both sides. So all that work to get y is equal to -3. And then, of course, x equals 3 plus 2/3 times -3 would give me 3 minus 2, which would be 1. So 1 comma -3 is the solution. Now, I guarantee there's a lot less work involved if instead you had isolated this one, right? Better to start by isolating the y in that equation, okay? But you will get the right answer no matter what, so long as you do your algebra correctly.